Hello everyone. Atoms Part 3 Bohr model of hydrogen atom continued. In this video, I will be discussing about the line spectra of hydrogen atom, the explanation given by Debroglie of the second postulate of Bohr and about the limitations of the Bohr model. So first we shall see about the line spectra of hydrogen atom. Now according to the third postulate of Bohr's model, when an atom makes a transition from a higher energy state with quantum number Ni to the lower energy state with quantum number Nf, the difference in energy is carried away by a photon of frequency nu if, such that we can write h nu if is equal to Eni minus Enf, where Eni and Enf are the energies at that state. Now using the formula for energy at a state, we can rewrite the equation as h nu if is equal to me raised to 4 by 8 epsilon square h square into 1 by nf square minus 1 by ni square, or nu if is equal to me raised to 4 by 8 epsilon square h cubed into 1 by nf square minus 1 by ni square. Now we can write me raised to 4 by 8 epsilon square h cubed as r, and r is known as the Rydberg's constant, and its value is equal to 1.03 into 10 raised to 7 meter raised to minus 1. So Rydberg's constant's value is very close to the value obtained from the empirical Balmer formula. This agreement between the theoretical and experimental values of the Rydberg constant provided a direct and striking confirmation of the Bohr's model. So for hydrogen spectrum, the Balmer formula corresponds to Nf is equal to 2 and Ni is equal to 3, 4, 5, etc. The results of the Bohr's model suggested the presence of other series spectra for hydrogen atom, those corresponding to transitions relating Nf is equal to 1 and Ni is equal to 2, 3, etc. Nf is equal to 3 and Ni is equal to 4, 5, etc. and so on. Such series were identified in the course of spectroscopic investigations and are known as the Lyman-Balmer-Paschen bracket and Fun series. And these are as shown in this figure. And this figure shows the transition of electron from each states and also the different spectral series. Now the various lines in the atomic spectra are produced when electrons jump from higher energy state to a lower energy state and photons are emitted. These spectral lines are called emission lines. On the other hand, when an electron jumps from a lower energy state to a higher energy state by absorption of photon, the process is called absorption. The explanation of the hydrogen atom spectrum provided by Bohr's model was a brilliant achievement which greatly stimulated the progress towards the modern quantum theory. In 1922, Bohr was awarded Nobel Prize in Physics. Now we can see the de Broglie's explanation of the Bohr's second postulate. The French physicist Louis de Broglie explained the Bohr's second postulate. That is, that angular momentum of electrons orbiting the nucleus is quantized in 1923, 10 years after Bohr proposed this model. Louis de Broglie argued that the electron in its circular orbit, as proposed by Bohr, must be seen as a particle wave. In analogy to waves traveling on a string, particle waves too can lead to standing waves under resonant conditions. And this is as shown in this figure. In the case of a string, when it is plucked, a vast number of wavelengths are excited. However, only those wavelengths survive which have not set the ends and form the standing wave in the string. It means that in a string, standing waves are formed when the total distance traveled by a wave down the string and back is one wavelength, two wavelengths, or any integral number of wavelengths. Waves with Other wavelengths interfere with themselves upon reflection and their amplitude quickly drop to zero. So for an electron moving in nth circular orbit of radius Rn, the total distance is the circumference of the orbit, that is 2 pi r. Thus 2 pi Rn is equal to n lambda. Now the equation for the de Broglie wavelength lambda is equal to h by p, where p is the momentum, and it is given by h by m into Vn. Therefore, we can write 2 pi Rn is equal to nh by mvn, or mvn Rn is equal to nh by 2 pi, which is the Bohr's second postulate. Now we can see the limitations of the Bohr model. The Bohr model is applicable to hydrogenic atoms. It cannot be extended even to mere 2 electron atoms such as helium. In case of elements having more than one electron, each electron interacts not only with the positively charged nucleus but also with all other electrons. But Bohr's model did not include this electrical interaction between electrons. Then second is, Bohr's model correctly predicts the frequencies of the light emitted by hydrogenic atoms, but the model is unable to explain the relative intensities of the frequencies in the spectrum. So this is the end of this video. In this video, I have discussed about the line spectra of hydrogen, the explanation of the Bohr second postulate by de Broglie, and also about the limitations of the Bohr model. If you have got any doubt, please comment in the section below. Thank you.